This is a production of Cornell University.
Good. And I'd like to thank Bob Langhan's Visiting Scholar program for hosting me here today, and of course all the folks at Cornell who always give me such a warm welcome when I visit. So light is the most important environmental factor for photosynthetic organisms, and I thought I understood it. I've worked with plants all of my life. I did graduate studies on light acclimation of wheat and also light acclimation and photo protection in an Antarctic green algae. So I knew light. But it wasn't until 2007 when I joined Heliospectra that was founded by plant physiologists. There were the two of us working with LEDs, and it was then that the light came on. And we grew a small engineering team along with a couple of plant physiologists, and that's when I started fusing engineering into my plant physiological research. Oops. So this is a photograph of the different colors of the sky. And when I saw this, it prompted me to start experimenting with spectral compositions to see if I could replicate these colors. And below is the panel of photographs I took of styrofoam in the back of a growth cabinet where I did these experiments. So it showed, one, that we can replicate these colors, and two, we have a really powerful tool now to create any kind of spectral condition that we want. I wasn't the first person to be obsessed with light quality. This is a cyanometer that was invented by de Saussure, and he used it in the Swiss Alps to measure the blueness of the sky. It was also used in 1802 by Alexander von Humboldt when he characterized the South American volcano. He did a complete physical and botanical characterization of the volcano, and he was able to classify the color of the sky as he ascended the volcano. And on the same note, and light changes. And I think when I saw this figure that was published by Lou Albright, it was shocking. Lou showed that there is a large annual variation in daily light integral on any given day in Ithaca, New York. And this is an annual variation. This is a 14-year study. So light is variable. The PPFD is variable. And on a shorter time scale, it can be seen here that light and PPFD, sorry, it's watts per square meter on the y-axis there, that we also see really short-term fluctuations in the sun. Now, these studies are usually performed to understand and improve performance estimations for solar energy systems. And so they look at these very fast fluctuations in the sun to see how they're going to affect the grid. So here we've got seconds on the x-axis, and you can see that if you take the average of this 3-hour-long fragment, it's 450 watts per meter squared, but we can see that it jumps from 100 to 700 watts per meter squared in less than a second. So this may not have implications for solar energy systems, but plants can certainly detect this. And it's made me really interested in dynamic lighting and fluctuating lighting for controlling crop growth. So at the same time that PFD is fluctuating, the spectrum fluctuates as well throughout the day. As the clouds pass over, you get a blue and rich spectrum under that piece of cloud, and then when that moves, it comes to a more flat spectrum. So this is a greenhouse in Sweden that I lived in for 3 days with my assistant, measuring light and the physiological state of the plants. Their basil was getting to the grocery store half dead, and they didn't know whether it was happening at the end of its life in the greenhouse or during transportation. So we monitored light for 3 days and just examined the environment, did physiological testing, and found out it was the temperature of the delivery truck. But during that time, I was able to study the spectrum and PFD during the day, under shade or under thermal curtains, etc. And that was a really useful study. So plants have evolved for 400 million years under fluctuating light. And this can be on a long or short-term time scale. So why not utilize this in large-scale growing? Also, why not use the intrinsic properties of LEDs to modulate our crops? So how is this done? Well, there are two systems in plants that sense, detect light, and then signal to the plant what to do. And I'm just going to quickly go through them here. So the first one is the photoreceptor system that we're all familiar with. And it induces responses ranging from immunity and defense right up to flowering. There are 15 different photoreceptors. We've got the oops, I did the button, which oops, there we go. So we've got the UVR8 here, which is the UV photoreceptor, primarily involved in defense and photoprotection. We've got the cryptochromes, which absorb from blue up until the green. And they're involved in biochemistry as well as circadian rhythm primarily. The phototropins are movement. They're another blue photoreceptor family. And the zeitlube is a timekeeper, also absorbing in the blue. We've got the phytochromes, which are just so well known and well characterized, and they absorb and are activated across the spectrum. A couple of these are reversible. Most of them are reversible, but primarily cryptochromes and the phytochromes are reversible using different spectra of light, and so they really do provide a molecular switch for us. So here we have the same diagram. We have the photoreceptors here. There is no green photoreceptor elucidated yet, but phytochrome absorbs in the green as well as cryptochrome, so in a way they do function in photoreception in the system. So we've got the photoreceptors, we've got the action. So these are the peak maximum for the action spectra for the various photoreceptors. And you can see that it goes down from 280 nanometers, which is the UVB area, right up to 733 nanometers, so the far red spectrum. Except right here there's a gap from about 600 to 660 nanometers, which is kind of interesting. But I came across a paper describing the action spectrum of PS2, of photosystem 2 photodamage, and it occurred right in this area. So maybe that has something to do with this, I'm not sure. Looking at the activation times, I work in engineering, so we're always looking at rate constants and timing and trying to do things as fast as possible. And so they work relatively quickly. When you see the next sensing system, you'll see that this might even be a little sluggish. So this brings us to the photosynthetic sensing system, or photosynthetic control as we know it. And when I did my PhD and master's, I worked in a lab where we looked at this in various organisms, from cyanobacteria right up to poplar, and looking at photosynthetic control in these organisms. So what does it elicit? It elicits a lot of responses that help sustain photosynthesis in a changing or fluctuating environment. So you've got light capture, photosynthetic efficiency, and CO2 assimilation. You've also got rapid accumulation of pigments to help protect the photosynthetic machinery. And when you grow under conditions where photosynthetic control is active, then you also have protection and defense. And in long term, you can actually adjust the height and other morphological factors. So what is this? So here is my very simple schematic of photosynthesis. We have two photosystems, photosystem 2 and photosystem 1, that work electrochemically in series. We've got a mobile plastoquinone electron carrier that transports the electrons from photosystem 2, where they're extracted from water, and brings them through a series of carriers to photosystem 1, where they reduce NADP to NADPH. At the same time, plastoquinone pool drops off protons into the lumen, and this drives in ATPase to generate ATP. So you've got the two chemical energy components that the plant cell uses. So what is photosynthetic control? Anytime you have a situation where you have light energy exceeding chemical energy utilization by the plant, you have an upset. And that upset triggers hundreds of genes and 26 different pathways that will help protect the machinery against this energy imbalance. So typically, this is done by subjecting the plant to high light, because then you're increasing the energy input. At low temperature, it works as well because you're decreasing the reaction rates of photosynthesis, so you end up with excess energy again. And when you have a nutrient deficiency, you're limiting the number of electron sinks. So again, you're pushing this energy balance in the chloroplast out of whack. And that is going to signal all of these responses. So during photosynthetic control, you've got the two main signals as the delta pH across the thylakoid membrane and reaction oxygen species, and the redox state of ferredoxin and thioredoxin. And there's a few others as well that aren't on here. So we can throw this out of balance using the spectrum as well. So this is where LEDs can come in. So PS2, we call it P680, absorbs preferentially at 680 nanometers, and photosystem 1 is P700, so it absorbs preferentially at 700 nanometers. Now we have something that we call PS2 light. PS2 light overexcites PS2 compared to PS1, and this is wavelengths below 680 nanometers. So any red or blue LED fixture used in plant growth is basically giving the plant PS2 light. How does the plant deal with this? It will adjust the stoichiometry of PS2, PS1 units. So they'll have more PS1 relative to PS2 to deal with this red and blue light. You never see it in nature. PS1 light, of course, is when you go up to the far red. And if you have a good balance, you should have a good stoichiometry of your photosystems and smooth sailing of the electrons right through to carbon metabolism. This is the same diagram, but just depicted a little differently. And again, I've got the time constants of these reactions listed. So we have light harvesting and charge separation, which is when the electron in photosystem 2 goes from water to the QB binding site. We call that charge separation. This occurs on femto and pico second level. Electron transport occurs on milliseconds to second time scale. And you've got carbon metabolism, which is primarily minutes to occur. So you have orders of magnitude difference in the rate constants for photosynthesis. And we can certainly drive LEDs at the millisecond and second timescales. You should theoretically be able to drive them at nanosecond timescales, but I've never seen that yet in a practical way. So we can utilize LEDs for this. So how do we do that? With pulse width modulation, which is a really popular way to dim LEDs. Here we've got the duty cycles for LEDs. So the duty cycle is the percentage of time the light is on. So at 100% the light is on, there's no off period. At 80%, you've got the lights on at 80% of the time during the period, 50%, 20, and then 0% duty cycle. Of course, the lights are all off, hopefully, although this can be a challenge sometimes for lighting fixture developers. And here we've just got sort of a pictogram describing this. So we can utilize this to help sort of unbalance the chloroplast to achieve these responses that might be beneficial. Warburg, or we can do the opposite, is drive it so that we've got efficient photosynthesis under other circumstances that might throw the balance off. Warburg found that 40 milliseconds of dark was adequate to oxidize the whole photosynthetic electron transport chain. So to keep photosynthesis continuing, you need give it 40 milliseconds of dark in a period, and you'll get all those electrons moving along to carbon metabolism, and the reaction sensors open and able to accept a photon. Tennyson later on, using a 680 nanometer LED, found that 198 milliseconds of dark in a period was too much. It decreased the rates of photosynthesis, and so we need to find the balance, and we need to understand the effects of pulse width modulation on photochemistry and photosynthesis. When you're looking at different fixtures and you call the companies, and I do this all the time, and I ask, are you dimming using pulse width modulation? And it's very popular to do that in human-centric lighting, but we're easy to trick. Plants aren't. They see a lot more than we do. Quite often they don't know. It's just something that they don't think about. So our question is, photosynthetic control is rapid. Can we use PWM to adjust this and play with this? One last thing before I move away from LEDs is the phase of pulse width modulation. This is a great study published by Shimada et al., where they use red and blue LEDs. So here we have 100% duty cycle. The R and B LEDs are running full time. Here we've got a 45% duty cycle where the red and blue LED are going on and off in phase. Here we have the red and blue LEDs, again a 45% duty cycle, but they're going off and on in different phases. And let me tell you, I've just designed a 6 wavelength fixture, so and got the engineers to make it so all of the LEDs, when we pulse width modulate them, will come on and off in phase, so that we don't have to do this. Because if we look at these Arabidopsis plants, you've got most growth, better performance it looks like, in the plants grown under the 45% duty cycle when they are in phase. So that throws a bit of a wrench into the works for light designers.
Yeah, so were those replicate plants?
You'd have to go to the paper. It's an engineering paper, probably not. They probably did, but no quantitative data.
Yeah. But those are like 5 plants that came out of the PWM.
Yeah.
Yeah.
Yeah. I'd have to actually read through and see their methods and statistics again. So there's hundreds of experiments of light quality and plants. And Porter pointed out in his 2010 paper that none of these experiments have been set up in such a way that we can actually quantify and compare the analyses. There are different wavelengths, different peak maxima, different temperatures, nutrients. There's no way we can generalize and sort of make a unified theory for LEDs and plant growth. So I'm going to show a bit of the data that we've generated in the lab over the last couple of years, and I just want to bring home 3 main findings that I think are really interesting. So looking at the different fixtures that we grew under, and we do all of our work under sole source lighting at RPI. We've got PFD here along the y-axis, and of course wavelength here. We've got the cool white fluorescence. Pay attention to this. You'll think about it a bit later, which is a nice, standard spectrum that we're all used to. Illumitex is this red line here. So there's a peak at 660, tiny little bit of white. You can't see it here, but I can measure it with my spectrometer. A little bit of green, and then the red or the blue peak here at about 450 nanometers. The Philips is 660 nanometers red, 470 nanometers in blue. The Veloya is a phosphor-converted LED. That means that it's a blue LED, typically, with a phosphor spread on the lens to broaden the spectrum. They're using blue, but they're using UV now as well for some of these phosphor-converted LEDs. And so here you've got a peak at about 440 and this broad shoulder over the green and red into the far red. And for those of you that aren't familiar with the spectrum, this is blue from 400 to 500, green, red, and far red. So the last one is Fionia. It's a Danish lamp. And we've got a peak here at 660 and a peak here at 434 nanometers. So we grew under all of these spectra. Our model organism in the lab is lettuce, and this is red lettuce ruxi grown under cool white fluorescent Phillips, Pheonia, and Valoia. And I'd like to just focus on these two. These are two red and blue LEDs. They look identical to the naked eye, but there's a 36 nanometer difference in the peak maximum of the blue LED. And look at the difference in the plants. They're significantly smaller, and well, we'll see some results in the next. Same PPFD, it's 200 micromoles. Same temperature, same nutrient solution, same CO2, same relative humidity.
The Swedish bulb mimic the Swedish skylight that would be more blue because of the increased scattering?
Yeah, this is done at RPI actually, but in Sweden, you can mimic whatever, anything.
But is the light blue because of the sun going through a shaded area?
Yeah, actually, and I have some data at the end of this talk, which I wasn't going to present, where I did spectral analyses on an island in the North Atlantic off Gothenburg, just north of Gothenburg. And yeah, it was very blue in the morning, and then it evened out during the day. And in the evening, again, there was also blue light present. So yeah, probably from the scattering. And it's always cloudy there. So probably a lot of blue light enrichment going on. So just to look at the fresh weight for green lettuce, red lettuce, basil, and the height on basil between these two red and blue fixtures, you can see that they're significantly different. So what is the grower to do? How are they going to choose even the blue and red fixtures when it can have such a huge effect on your crop? I was thinking that the Pheonia would be really good because it had a lower blue, and I thought, well, that will activate a lot of the biochemistry and sort of thickness of the leaf, but it was actually not a good. The plants were significantly smaller, and we withdrew it from our trials after 2 or 3 goes. And we replaced it with an Illumitex fixture, which I showed you. It's essentially blue and red. It has a tiny bit of white, which gives a little bit of green to the spectrum. So here we have red lettuce ruxi again. The LED treatments, there was no significant difference in the fresh weight. However, this cool white fluorescent did have significantly lower fresh weights at day 16. The anthocyanin was highest, that we always see under the cool white fluorescent. So we're now delineating which one of those peaks are actually responsible. So we've gone through the green. It does give a bit, but I think it's actually going to be a combination of a couple peaks in that spectrum that is responsible for this. So we have high anthocyanins here, the red pigment, and we have extremely low biochemistry occurring in the under the Valoia fixtures, and we've measured carotenoids, chlorophylls, and anthocyanin, and we see the same in all. So looking at the anthocyanin, we tried different cultivars. So we have ruxi here. We've got anthocyanin concentration there. Red salad bowl, regis, and red sales. And we can see in more cases than not, under the phosphor-converted spectrum, you have lower anthocyanin concentrations. So we threw in even more cultivars. And here we have our standard ruxi, and we had the Salanova red butter and red oak leaf. I'm calling the Illumitex here red, blue, and white, because usually when I speak at conferences in the engineering world, I don't like to give the name away of the fixture. We've got the Valoia phosphor converted, cool white fluorescent, and we've got the Phillips red and blue. Look at the difference in the morphology, the leaf size. When you touch these plants, you can feel the difference. The red butter under the Illumitex is very hairy, and the Culinary Institute would say has bad mouthfeel. It's not very pleasant to eat. But that changes depending on the spectrum. Look at this under the cool white fluorescence. The plants can't even stand up, and this is repeated. We've repeated this now about 6 or 7 times, and we're seeing the same results every time. So one common thread, because there's no commonality here, but one common thread is that under these phosphor-converted fixtures, there is poor anthocyanin concentration. So this led to the question of, is it something specific in the phosphor conversion of LEDs that is responsible for this? And I met Wouter Sauer at several actually engineering conferences, and he is an engineer that works for LumiLEDs, and I discussed this problem with him, but one of the problems was that I could never really see if it was the phosphor conversion, because the other LEDs that I'm comparing to have different spectral ratios. So it might be the spectral ratio and not the phosphor. So we spec'd out some, and these are just photos of different phosphors that I took at a trade booth at this conference. They're using up to 5 different phosphors for one LED to actually get a different spectral distributions. It's quite fantastic. So Wouter and I spec'd out some fixtures that had roughly 20% blue, 20% green, and 60% red. We find that's a really nice spectral ratio to grow under. And so we achieved that. So we have lime. These are my growth cabinets here. We've got what we call the lime LED, the green, the purple. Of course, there's no green. The Valoya. And then we have direct emission LEDs that we built ourselves. And at this point, we're just running them on an RGB, red, green, blue program. So our numbers are pretty good, close as we could get them, and here we have the spectral distribution. So we've got photon flux density and wavelengths here, and we've got our RBG, so we've got the red at 660, green at 530, and blue at 450. We've got the green and the lime LEDs, which are these lines here. All slightly different. We've got the Valoya, which is this big one, and that's it. And the purple, of course, has no green. So where are we seeing differences? So rather than finding commonalities in the plants, I'm looking for commonality in the spectra. So what is it about this spectrum that is causing this? And so we see the Valoya has very little green, and you're going to see why this is important, compared to the lime and the green. It's got this big area here, right where the action spectrum for photo damage is. But then you'd think it would make anthocyanin to protect itself, but it's not. And then it's got a little bit of a difference here in far red. I didn't take that into account when I spec'd the lights. That was my mistake, because there's quite a difference there between far red between the fixtures. So let's look at some data. So this is essentially phosphor converted versus direct emission LEDs. And the yield is greater for the lime and green and Valoya. However, the anthocyanin is much lower. So not all phosphors are created equal. So the spectrum matters. Anthocyanin is more spectrally sensitive than yield, and not all phosphors are created equal, which is great. So the next work was, can we use the spectrum to modulate plants? So here is a Valoya grown plant and a cool white fluorescent plant. What happens when we shift a plant from a non-biochemically active spectrum to a biochemically active one? And here's 24 hours. We were able to increase the anthocyanin concentration 18-fold. And I've got a small movie here.
In just one day.
24 hours. This is a time lapse of 48 hours. And again.
Tessa, have you also conducted any taste tests on the different plants within a single cultivar?
No, not officially. We all have our favorites, but I would love to do that. Absolutely. So I'm hooked. This has grabbed me. And yes. No, unfortunately not. I'm in a semiconductor lab, so I'm kind of building it up. I've got a spectrophotometer, and I've got, this and that. I've got access now to HPLC, but I would love to. Actually, I did the shift experiment back, and it's about 24 to 48 hours. Just depends on the life history of the plant a bit. Yeah, but we can shift it back and change the morphology changes as well. We can just move it back and forth. So it kind of, why not grow a plant under LEDs that produces large biomass and at the end finish it off so that we can pack it full of nutrients and maybe save energy at the same time, is sort of my theory. I'm going to have to speed up here through the last bit. So one interesting thing, I've worked a lot in photochemistry. I'm really interested in energy in the chloroplast. And this is my pulse amplitude modulated fluorometer that I got out and used during the shifts to see what was happening to the plants. So we've got effective quantum yield, so the probability that a photon will be used in a photochemical act. And here we have, the lower it is, the less efficient it is. So here we've got the plants at time 0. They were pretty good at 0.64, it's reasonable. But when we shifted, and this is 1 minute after the shift, we saw an increase in effective quantum yield throughout the 24-hour shift, and then we shifted it back here, and it decreased. And again, we were able to measure this within 1 minute. And the reason it took me a minute was because I had to jump behind a laser curtain and press start on the computer. Otherwise, if I had an assistant at that time, we could have actually done it a bit faster. Non-photochemical quenching is the dissipation of absorbed light energy as heat, typically through the xanthophyll cycle. Indicates that there's something wrong, there's a blockage, and it has to get rid of that energy. During the, before the shift, it was normal values, but high. During the shift, it went down, shifted it back to the original spectrum, and it goes back up. This makes really good sense, but it shows how we can detect this, and this is fantastic. So I started with a bunch of undergraduates building detectors in the lab. So this is the first prototype. This is the excitation light. This is a photodiode picking up the chlorophyll fluorescence. And you can see how close we're working with to the plant. Here is my very expensive German pulse amplitude modulation fluorometer. So here we have low temperature photoinhibition. The open circles are measured using the ERC student device, and the dark circles are my commercially bought device. We're right on measuring stress with both detectors. Excellent. But let's move further. Second round of students came in. This is our second prototype. We've got the excitation light here. We've got the photodiodes there. We're working at 40 centimeters from the plant, and we're able to detect about a half of a 1020 flat. This was pulled from an engineering student's report, so you can see that they've had to indicate that this is a plant. So it's a lot of fun.
Actually more than one plant.
It is more than one plant. I should have docked marks for that, I guess. Good point. So we had a dual of the centers here. I'm dark adapting plants, which is a bit of a pain, measuring the maximum quantum efficiency of photosystem 2. We can see during shifting Basel from 23 degrees to 5 degrees, we get the standard decrease in FE over FM. Using the student sensor, we're seeing, again, the same thing. Then I thought, okay, this is it. I'm sensing all the time, because we have these sensors, and I've got a group of students coming into the lab to build more this summer. Hopefully we can get some at Cornell as well. So here we've got a 16-hour photo period, and this is the signal emanated from the plant at 740 nanometers, and this is the signal that we usually detect with the PAM, 680 nanometers. So 640 is a bit more complicated signal. I can talk about it more to anybody who's interested, but for the sake of time, I won't now. One thing we noticed was this oscillation over and over again. We've done this about 10 on lettuce and basil, about 10 different crops. And what we see is this is the chlorophyll fluorescence yield. When it's high, photosynthesis is downregulated. When it's low, photosynthesis is running smoothly. So in the morning, when the lights come on, it's getting all the enzymes ready for carbon assimilation. And then it flattens out during the day. Here, about 10 hours into the 16-hour photo period, chlorophyll fluorescence goes up. So photosynthesis is being downregulated. Now, what should we do? Should we turn the lights down and save energy when it's apparently not using it in photosynthesis? Or do we use spectral combinations to try to mitigate this? Open the stomata, force it to not have that afternoon nap. So those are two questions that I have that I'd really like to work on together. And here we have death, which again, the students forgot to water plants, and actually all of this data is uploaded to the cloud, and I can check it regularly from home, and I can tell exactly when they didn't come in and when they did. So they're learning. They're learning. So with circadian rhythm, because we're seeing that here, what they do in animal systems is they say, okay, put it in the dark, continuous dark, and see if you see that oscillatory pattern. But I can't do that with plants. So we put it in continuous light, and here's a 24-hour. Here we've got another death by dehydration experiment, and we're seeing the same oscillation. This is super exciting. And so one last thing, we did this during growth of basil. We can see similar oscillatory pattern happening here, and of course an increase in growth, well, in fluorescence, because they're filling out the flat and they're getting a bit taller. So whether in a greenhouse or a plant factory, light definitely matters. And maybe we should be thinking, now that we have the ability to turn off and on a light source at 200 nanoseconds, maybe we should be thinking about how to use that to modulate plants that are used to this. So we need more knowledge. Plants acclimate in a different way. We need to understand that. And we need to integrate this into control systems with the potential outcome of saving energy. So I couldn't have done this alone. My lab is 3 years old now at RPI. And I just want to thank all of the support staff, Bob Karlichek, has been really supportive of this work. And of course, all of my undergraduate students that have contributed to the work that I've shown today. Thank you very much. Happy to take questions. Dale.
Can you go back to 31? It's the pan versus
That one? That one?
No, go towards the end.
The one with the oscillation on it.
Right.
Okay, that was just the student sensor, no pan sensor.
Blue line is.
The blue line is, we have 2 photodiodes in it. So we've got a 680 filter for the photodiode and
So
740.
is this non-detectable?
Yeah. Well, that's why I'm going to be testing it ASAP. So, as soon as we automate it.
Advantage of student sensors for the plant and not just simple.
Yeah, we're looking at several plants. And we want to move further and bigger, of course. And that's why it's so important to speak with engineers.
So in a practical greenhouse situation, this version of the sensor may be more useful if you're able to look at it.
Yeah. And of course, the field of view will be dependent on the height, right? Also the optics of that photodiode. And the excitation light, because the excitation light has to be, has to illuminate the whole thing. And it's been a challenge. Most pan parameters work with saturating pulses that in the old textbook said they were the same intensity as a bright sun, which would be about 2,500 micromoles. But now if we're using saturating pulses of 8,000 to 20,000 micromoles, and if you try to use that in this kind of sensing, you'd kill the plant. So we're not saturating, which is a bit more complicated.
Our colleagues at Geneva may have a question.
Oh.
Is there, Geneva, do you have a question?
I guess I do. I'm curious, when you did your 24-hour spectral change experiment in video, that was kind of in a younger leaf or plant type. I'm curious if you think a mature plant type would have the same capacity to respond as quickly.
Yeah,
and if you're thinking of using it to finish plants in a controlled setting.
Yeah, we've done it with larger plants as well. Like anytime I have anything going on, I shift things. And yeah, we did see it under older plants as well. Like 21 to 28 day plants. We don't usually grow them beyond that.
And that was Hannah in Crick's lab.
Oh, hi Hannah.
Any other questions? Tessa, I'm curious, these lighting companies, these LED lighting companies will talk about light recipes. They're like, oh, here you go, grower, here's a lamp, now you can develop a light recipe for your crop. How easy is it to develop a light recipe Wouldn't there be like millions of combinations? How do
There,
you do that?
if you have a red and blue LED, it's, it's like, do you want 20% of blue or 80%? That's kind of the light recipe. But when you're working with, I spent 8 years developing light recipes with 710 lamps. I ran over 60 experiments. And it takes a couple of years, really, to be confident that you have a good recipe. I don't really like calling it recipe either, but I'd rather call it a light protocol or something like that.
Yeah, how about algorithm?
Or algorithm, we've discussed that before, because recipe sounds like I'm just in the kitchen cooking up my flour and butter, and it's harder than that. Yeah.
Those protocols would also really only be transferable, I suppose, if it was in a growth chain. Because if you tried to use them in a greenhouse, whether you're in Tucson or New York or Sweden, I suspect it's terrible.
That's right, but if there's a lot of darkness, like in Sweden, it's like sole source lighting. Essentially, you never see the sun when you've got the lights on. But any tweak in your nutrient solution, in your temperature, and any sort of growing condition will alter it as well. So what I find, if someone takes it into their sole source lighting area, it would be different if they didn't replicate my growing conditions exactly. Yeah.
Following up on Phil's question, do you think there's potential to manipulate these sequences even in the presence of a large amount of background sunlight?
Sure, and what I envision for that is, and my greenhouse measurements in Sweden did show that spectrum changes throughout the day, so we did develop some dynamic lighting there, which I can't discuss or it'll have to kill me. So, but what we did, but what I would like to do is, as sort of the blue region, once we get our spectrometer up and running and automated in the greenhouse, we'll be able to record the spectrum and then perhaps utilize the LEDs to bring the spectrum up to a set point that we know is beneficial for our crops, so that you have stable, consistent supply of your crop. Yes.
I'm curious if that oscillation that you see, the changes you encounter.
Well, this is when I have it with no photoperiod. So we're still seeing that oscillation.
Was it entrained to the 16-hour on, 8-hour off, and then to the continuous light?
Yeah. Yeah. And I've really got to get the students to water.
You're a horticulture student.
And as you saw in the photos of my lab, where are the plants? They're all in front of oscilloscopes or walking amplifiers. So, yeah, in the fun run.
Any final questions?
This has been a production of Cornell University, on the web at cornell.edu.